Welcome listeners again to the second part of our discussion on stratigraphy, which is also a topic in our series of discussion on fundamentals of geology. So again going into the second part that deals with the rest of the principles that are used. So we have seen the law of superposition, law of original horizontality, law of lateral continuity, a law of cross-cutting relationships, and how these sequences, or you can say the laws of this horizontality or continuity, are getting affected by the presence of faults and unconformities, and how these events of geological events or the tectonic events or your sedimentary events, be it your fault or unconformity, these events are giving you an insight into the past geological history, that whether there has been some event of erosion, whether there has been some changes in the mean sea level, whether there has been some changes in the tectonic, or some tectonic disturbance was there. And related to that, it also occurs to me that apart from the understanding of this principle, it is also necessary that when these principles are somehow getting violated, be it locally, obviously these are principles that can be applied across region for correlation, but locally these principles may get violated due to some kind of discontinuities that are present. So apart from these four principles that we discussed, along with the unconformity idea of unconformity in the first part, in the second part we will now start with the principle of inclusions, where your rocks containing fragments of another rock are obviously younger than the fragments they contain. Like you can see in this diagram that your for example, in granite you have some remnant of some older sandstone like this. So I will say that the granite is younger with respect to this sandstone. Why? Because that granite has intruded and engulfed this sandstone in its center, and the surrounding sandstone, you can say, might have been melted due to the intrusion of this granitic body. So likewise, if I look at this simple photograph of amber, where you can see the presence of flies in these crystals of amber, so obviously you will say that the fly is older with respect to the amber. So now the amber is engulfing the fly within it, or it is preserving the fly within this amber. So inclusions are rock fragments within a larger rock body. When we are talking about rock bodies, in case of paleontology or in biological sciences, it could be a biological species as well, like this amber. This is also an inclusion within the amber. The fly is an inclusion within the amber. So the principle helps to determine the relative ages of the rock formation by establishing the sequence of events based on inclusion of older material within younger rocks. It aids in understanding geological processes such as erosion, deposition, and rock formation. So this example again you can see. So this schist, which is possibly the most the schist here is the oldest rock, followed by the formation of your sandstone, for example, above this unconformity. So this unconformity, as it is a period of erosion, so it might also transport some fragments of the underlying schist, then it will get embedded into the sandstone, and both the sandstone and the schist in totality, they are getting embedded in this molten granitic magma that got solidified. So after solidification, you will get granite as the outer or the dominant rock. Within it you will get some fragments of sandstone and schist. So you can say that schist is the oldest one, followed by the sandstone, followed by the granite, which is the youngest rock in this particular sequence. Then you can also think of principle of faunal succession, where your fossil organisms succeed one another in a recognizable order through time. Like I was giving the example of trilobites and dinosaurian eggs when we discussed about unconformity, that there is a specific age difference because they belong to two different era. One is Paleozoic trilobite, another is, for example, Triassic dinosaur. So in that case, there is a age difference, allows geologists to correlate rock layers based on the fossils they contain. So you can correlate between two rock layers in some distant part in a region just basis on the presence of a specific fossil in that rock. So it also provides, because they are very reliable indicators of age, because every fossil record represents certain age, like we discussed about the presence of trilobite prior to the Permo-Triassic extinction when we discussed about geological time. So it helps in reconstructing past environments and understanding evolutionary changes over the time. Like you can see the sutures that are present in the ammonoid, they were simpler earlier, the suture were very simpler, followed by complexity in the suture, and now this one, a very beautiful one, but a very complex kind of suture that you can observe in your ammonoids. So it enables the creation of biostratigraphic zones for dating and correlating rock formation. Also, you can have an idea that how a species might have developed over the time. Principle of incomplete record. The principle of incomplete record acknowledges that the geological record is not always a continuous thing, and you may have gaps or missing layers in it. Geological processes such as erosion, non-deposition, and subsequent removal of rock layers can lead to discontinuities in the stratigraphic sequence, like we have seen in case of the unconformity. These gaps in the rock record, known as unconformities, like we discussed, can be caused by various factors including tectonic activity, sea level changes, and weathering. And unconformities represents periods of time during which no sediment has been deposited. Understanding and identifying these unconformities are extremely crucial for accurate interpretation of geological history. Then also the principle of base level or base level changes. The principle of base level refers to the level below which a stream or river cannot erode its valley. So the base level can be local, for example a lake, or ultimate, which is obviously the mean sea level. So that is the ultimate base level below which a river can't erode. Apart from glaciers, glacials do erode below the mean sea level, which are also referred to as fayets. We will be talking about that, talk about glacial geomorphology later on. So streams adjust their profiles to reach base level, resulting in erosion upstream and deposition downstream. Changes in base level can lead to changes in sediment deposition, channel morphology, and landscape evolution. Understanding base level helps in interpreting the evolution of river system, landforms, and sedimentary environment. So here I can look at this diagram. Here you can say that there is a lake. So obviously the river profile is adjusted to the lake, that is the local base level, but finally the river profile will be adjusted to the mean sea level. So it is again a basis where you are assessing the base level, you are assessing it at a localized zone, or you are assessing it with respect to the mean sea level. So the sediment source area, that is obviously subject to processes of erosion, and finally the lowest level of continental denudation will be your mean sea level, and that will be treated as your base level in this case. So that is again the principle of base level, that whether you are assessing the level of erosion with respect to some localized base level, or you are taking the regional base level, which is obviously, or the ultimate base level, that is your mean sea level. Principle of accommodation, that how your sediments are being accommodated into the sea, or even in some cases, I mean, if I again talk about local accommodation, I can think of also lake sediments. Then describes how sedimentary layers adjust to irregularities in the surface on which they are deposited. States that sediments will be deposited to fill depressions or irregularities in the substrate. Leads to formation of features like channels, dunes, and unconformities. Helps in understanding the shape and distribution of sedimentary deposits in relation to underlying topography, that how the topography might it have been resulted in controlling the deposition of the certain sedimentary layers above the topographic levels. So there also your base level can change depending on the sea level rise and fall. So if there is marine transgression, that means the sea level will move up, so your base level will also move, so that is your sea level 2. And if there is, for example, a fall in sea level, that is sea level 1, so your base level will also go down. So your marine stratigraphy in case of your marine sediments are determined by the sediment flask, and the accommodation determined by the eustatic sea level changes, be it rise or fall. It also reflects the amount of uplift and subsidence. So this is a shelf, you can have an uplift or subsidence, and that will also have an impact on the mean sea level changes over a time. Then you have the principle of preservation potential. It focuses on the likelihood of certain types of organisms or materials being preserved in the fossil record. Like if you remember, we discussed about the soft and hard part in the formation of the sedimentary rocks, that you soft part when an organism, and marine organism for example, dies, be it your coral, be it your some kind of snail, the hard part gets preserved, or it settles down at the bottom of the sea, and the soft part, after the death of that organism, it simply leaves the rest of the hard part. So your hard part might get preserved in a process like that. For example, the formation of a biochemical limestone. So it recognizes that all organisms, not all the organism or material, have the same chance of becoming fossils due to factors like size, hardness and environment, but it help paleontologists understand biases in the fossil record and interpret it accordingly. It is not likely that if in some rock record you are not getting any kind of a fossil, so that does not mean that there was no organism that was prevailing at that time, but it reflects rather that in that time the organisms that were prevailing were not preserved due to, for example, lack of hard part, like we discussed in case of your snails. So lack of any hard part or lack of any, you can say, vertebrate, like we get to see in invertebrate fossils sometimes, that some of the invertebrate fossils they have been lost in the fossil record, but rather vertebrate fossils, they occur very beautifully all over the rock record. So it actually means the presence of bones, presence of solid parts will be more, there is a chance of a fossilization of these parts more in nature rather than only soft parts. But soft parts also get preserved, that you can also think of the giant woolly mammoths in the that we found in different Siberian glaciers, and the soft part are so well preserved that they look like that you have kept some material in freeze for a couple of days. So this principle of preservation potential, it also guides the selection of sampling strategies and locations of fossil hunting or excavation, and it acknowledges that the fossil record is incomplete and may not fully represent the diversity of the past life. Like I was saying, that even if there is the diversity, it is not necessarily that all the parts or all the species will be fossilized in the same manner. Some of them might get excluded during this process of fossilization. Then principle of cyclicity, like we have discussed about rock cycle, Wilson cycle, we will be discussing about water cycle in a few lectures from now. So these are all these natural processes. There has been an interpretation that all natural processes, they actually run in a some kind of a cycle, and they are pretty well balanced as well. Otherwise there would have been some changes in the topography, changes in the rock record, changes in the means you can say the overall architecture of the earth to larger extent, if there is some kind of balance is not existing. So it recognizes the principle of cyclicity, it recognizes repetitive patterns in sedimentary sequence. Sedimentary layers often exhibit cyclical variation in thickness, composition or fossil content. These cycles reflect recurring environment and climatic changes over time, such as fluctuations in the mean sea level. Analysis of cyclical patterns help geologists interpret past environmental conditions, infer long-term geological processes, like that rock cycle we discussed, like the Wilson cycle we discussed for the opening and closing of sea, rock cycle for the formation and destruction of different types of rocks, and the water cycle we will be discussing in a few lectures from now, and that will show you that how your overall your water budget is getting controlled from your evaporation, precipitation, recharge and discharge of groundwater, how these all things are related to one another. Then possibly the most important or very much useful, I'll not say important because all other principles are also equally important, but I'll say useful in terms of application is the Walther's law. That was formulated by German geologist Johannes Walther in the 19th century, states that the vertical succession of facies means types of sedimentary rock observed in a sedimentary basin reflects lateral changes in the environment as well. It also suggests that environments adjacent to each other horizontally will succeed one another vertically in the same order based on the concept of facies, which are distinct sedimentary rock types deposited in specific environments such as marine, terrestrial or transitional environment. It helps geologists interpret ancient environments and reconstruct the spatial distribution of environment within a sedimentary basin. Now, so if I say that you are somewhere, you are getting beach sandstone, offshore siltstone and basinal shale, then the presence of siltstone above sandstone and shale above your siltstone, it give you an idea of the transgressive phase, and in the opposite hand, if you are getting siltstone above your shale and followed by sandstone above your siltstone, then you can say that you are having a phase of regression. But the thing is that always whenever there is a marine transgression, what is happening, that obviously these rock types, they are getting deposited, or these rock types are formed in an horizontal manner, like when we are when the sea is transgressing from, for example, this is your coast or the coastal margin, the sea is transgressing like this through a span of a couple of 100 years or a couple of 1000 years, it is spanning like this. So here it will deposit certain rocks, here it will deposit certain rocks, here it will deposit certain rocks. So what is happening horizontally, because it is low dipping, horizontally some sediments like this one, sandstone, siltstone, shale and limestone, which you remember that limestone are strictly marine in deposits. You cannot form a limestone in a simple continental region. So there has to be an event of some kind of marine transgression or some changes in rise in the mean sea level to form limestone somewhere. So if I am getting some association of like this limestone, then lagoon deposit, limestone that reflects reef deposit, shale that reflects lagoon deposit, siltstone that reflects near shore deposit, and finally sandstone that represents beach deposit. Fine. So as the water is rising, that means there is marine transgression, the sea water is moving towards further within the continental shelf and finally your continental margin. In that case, what is happening means coastal region, as it is the marine transgression is happening, so now it can deposit limestone further inside into the coast. Again, if there is a rise, again it can deposit limestone inside the coast further. So likewise, if there are 4 such periods of continuous changes in the mean sea level, what you will get finally, that there will be these zones continuously that are placed horizontally, as well as if I now take it from bottom to top, they are also placed in the vertical manner. So from this we can say that whatever rocks they are present in this particular sedimentary environment, like that of a beach environment followed by near shore, then lagoon and reef environment, continuously the environment of sedimentary deposition is also changing. If they are associated horizontally, they are also associated vertically. So there is no question of its change. So whatever sedimentary rocks that are present horizontally, there has to be a correlation vertically as well. So that's what Walther's law is all about. Similarly, in case of a marine regression, in case of limestone that is getting deposited here, will get away from the shore further and further away from the shore, still you will get this sequence of limestone followed by siltstone, followed by shale and sandstone, and it also give you an idea that how the mean sea level has changed. So not only the correlation is important, it is also giving you an idea of the depositional environment, which is directly related to your climatic conditions at that point of time. So here you can have a rock record like this in a river as well. Also you will get sediments like self deposit, block deposit, pro delta deposit, distal bar deposit, mound bar, and beach and dune sandstone. That is also possible when, for example, a river is finally going to meet the sea. So if I take a complete cross section of that geological record, I will get this kind of sequence, and this sequence is also actually present horizontally. That is why they have been preserved vertically as well. So finally, the principle of correlation. This principle allows geologists to link rock layers from different locations based on similarities in lithology, fossils, and other characteristics. It enables the establishment of a chronological framework across geological formation. It also facilitates the understanding of regional and global geological history. It helps in the correlation in identifying equivalent rock units which are not present side by side. Some record is present here, some other record is present here, but they can be correlated basis on the idea of principle of correlation. Various methods such as lithostratigraphy correlation, biostratigraphy correlation, chronostratigraphy correlation are used to establish connections between rock layers and geological formations, and correlation is extremely essential for interpreting geological record, studying ancient climates, and understanding the distribution of natural resources. So just to look at the different methods, lithostratigraphy, when you are doing lithostratigraphy, you are depending on lithostratigraphic units, individual stratigraphic records, that is the lithology, means the rock type, sandstone, shale, limestone, this kind of information you need. Then if you are doing pedostratigraphy, you are relying on pedostratigraphic unit, that means buried soils or soil profiles. You are looking at the different horizons of soil that is related mainly to establish the and correlate soil profiles, and also or to means identify the environment in which a particular soil profile or soil horizons were formed. Then you have extremely popular biostratigraphic correlation, which includes the delineation of biozones, and it is solely based on the fossil record or the fossil content in a particular rock sequence. Chronostratigraphy, it means you have to have a very distinct time connotation to it. So time relationship, so based on the chronostratigraphic records, you can divide your geological time into period, epoch, and age. You have geochronostratigraphy as well, where your geostratigraphic unit, system, series, stage will give you some time relationships. Then you have magnetostratigraphy, which relates to the magnetic reversals on the earth, that how many times the north pole and south pole has switched its places over the geological past. So that is again based on the magnetic polarity, that how this north and south pole are getting aligned over the time. Chemostratigraphy, which is based on the isotope zones, that means you need to have very reliable chemical signatures, then only you can identify the isotope zones. And finally, sequence stratigraphy, which is dependent on allostratigraphic units, uniformly bounded packages. When there is no discontinuity within in that particular rock sequence, you can use the whole sequence under the sequence stratigraphy. This is very commonly used. This Walther's law is also and very effective, you can say, principle within the idea of sequence stratigraphic correlation. So here I would like to conclude my discussion on your stratigraphic correlation. Next, after this we will start our discussion on different geomorphological features across the earth. So thank you.